Claim is for every observable A, this relationship holds, right? And omega of t is a state that's represented by, let's say, density matrix M of t. So what's the proof of this? So let's work with the left-hand side. So this right here, this is given by the trace of A, which is a function of t, times M, which is a function of t. And notice I could write it as M times A as well, because the trace of AB is equal to the trace of BA. Now if I differentiate this with respect to time, well, I can pull the derivative inside the trace, okay? And so this becomes tr of dA by dt times M plus A times dm by dt. Now, we've got, on the other hand, that dA by dt, well, dA by dt has to be, by definition of how A evolves in time, it has to be the quantum Poisson bracket of H with A. It's got to be equal to that. And also, M of t, so from the Schrödinger picture, M of t must evolve according to ut m0 u minus t, where ut is defined to be the matrix exponential of minus i t big H over little or h bar. Okay? And if we differentiate this, we find that dm by dt is equal to minus quantum Poisson bracket of H with M. Okay? And also, as a reminder, the quantum Poisson bracket and the commutator are related by this relationship. Okay? So, let's carry this on. So using the relationships we talked about, this is going to be the trace of this plus or minus A times H with M. Okay? Now this is looking very similar to what we're after, right? This should be basically the same. So we want to show that this other term right here is 0. Okay, we want to argue that this guy right here is equal to 0. So how can we do that? Well, we've got that the trace of A, so this is equal to this times by I over H bar. Okay. Now this is AHM minus I over H bar trace of AMH. Okay. Now, okay, we're a bit stuck because we can't just swap these two around, right? If we want to use the fact that trace of AB is equal to B times A, then we have to kind of group it. We'd have to call this one matrix. So we know that trace of AHM is equal to the trace of M times AH, right? So that's fine. But yeah, we have to be really careful. Basically, the trace is invariant under cyclic permutation, and this is not a cyclic permutation. So it looks like we're stuck. Okay, let's look at this instead. So trace of, so HA minus AH times M and I over H bar. So can we say anything about this? Well, let's do this. Let's actually expand everything out. I think that's the easiest way to tackle this. And then in hindsight, we might find a shortcut. So that's sort of the optimal path to take. So let's factor I over H bar out of everything. This is going to be trace of HA minus AH into M minus by trace of A into HM minus MH. Okay. So this is going to be trace of, so we can put everything back in. So this is HAM minus AHM minus AHM plus MAMH. Okay. So, can we simplify this? I want to simplify this so that, okay, so these two cancel. Bang, bang, these two cancel. And we're left with trace of HA minus AH into M. And this is precisely trace of Poisson, commutator of HA M, right? We could, so I'll bring the I into here. And so we're left with d. So the total time derivative of the expectation is 1 over h bar times the trace of I commutator HA with M. So this is nothing but the expectation of this in the state omega t. And then finally multiply by h bar, and we get what we were after. Okay.